اناليتيكس والبيزنس انتليجنس اللي كانت هي تبارك الله زوينه بزاف. خدموا على واحد الداتا سيت عندها علاقه بالاي كوميرس في واحد ستور مغربي. دونك كان فيها السي يوسف والسي عمر فكري فوالا. خدموا ببور بي اي اكسيتيرا. النهار الرابع اللي هو الاربع اللي فات كان اباوت الماشين ليرنين، البيزكس ديال الماشين ليرنينغ، يعني الاساسيات ديال التعلم الالي. كانت حتى هي واعره بزاف. اللي كان انيماها السي محمد، اللي هو الصديق ديال السي ايوب، وكذلك الصديق ديالنا العزيز السي زكريا فوالا. وحنا اليوم في النهار الخامس اللي معنا يعني واحد جوج ديال الاصدقاء اللي عزاز عليا، السي ايوب بن عاشور اللي هو اي انجينير انترن في واحد ستارت اب ولا كامباني، ما عرفتش اكزاكتومون وات از دي اي سي اي، المهم كاينه في يو ام سي سبي ديال بن قرير. ومعنا كذلك السي يوسف مراد اللي هو سي تي او ديال واحد ستارت اب اللي سميتها تينيس اي اي. سي تاع لوريا ديال لينسيا فوالا. والسي ايوب سي تاع لوريا ديال لونيفرسيتي اوروميد في فاس. باقي نشوفوا معنا النهار السادس غادي يكون اباوت الان ال بي اللي هو ناتشورال لانجويج بروسيسين. غيكون معنا السي قابيل اللي هو واحد الدكتور من يو ام سي سبي ديال بن قرير. تبارك الله سي ان اكسبير في الان ال بي. غادي تكون الاربعاء الجاي. تنتمناو تدخلوا لليان ديالنا اللي هو لوما lu.ma/mds وتسجلوا، باسكو كان وقع لنا بتي بروبليم في داك ليفينمون وكانت تمسح دونك ما فيش بزاف لي زانسكريبسيون كوم سا باش تقدروا تحصلوا على السيرتيفيكا ديالكم منين نساليو ان شاء الله هاد لا سيري اللي سميتها فروم اي اي تو فروم زيرو تو اي اي هيرو، اللي اخر سيونس غادي تكون ميركودي 23 جويي. نهار السابع about reinforcement learning and autonomous agents. نهار الثامن about data engineering from zero to hero تتسمى ال 101. ونهار التاسع how to build your first chatbot using RAG. وغادي نشوفوا فيها الاز ال ال امز وغنشوفوا بزاف ديال الحوايج. واخرها احلاها هو النهار العاشر اللي غادي نهضروا على الاي اي اجنتس 101. ما نتمنى ما نكونش طولت عليكم. بالعاني بغينا نديروا هذه المقدمه باش تتبقى، باش كذلك تتمشيو تتشوفوا بوتيتر شي واحد يكون انتريسي بشي تيماتيك من هاد لي تيماتيك اللي سبقوا، وسيروا شوفوهم في يوتيوب باسكو اي حاجه تتبقى عندنا مسجله باش يقدروا الناس من بعد الاجيال الصاعده يستافدوا حتى هما من هذا الشيء. لي سيونس ديالنا تيكونوا 50% تيوريك، صافي دير سلايد سي دو لا تيوري لي فوندامونتو، و50% تتكون براتيك، يعني تنخدموا على لي ورك شوب وتنحاولوا ان يكونوا معنا دو سبيكرز باش كل واحد يعطينا واحد الاوفر فيو من المنظور ديالو. دونك باش ما نطولش عليكم جانفيت الستيج سي ايوب ولا سي يوسف راهم معنا دابا. منين تفضلوا قدموا راسكم، بارطاجيو لو سلايد. the floor is yours. Thank you very much.
ثانك يو. شكرا بهاء، شكرا على لوبورتينيتي. بعدا السلام عليكم كاملين. بون اليوم غادي نكتشفوا لو ديب ليرنين دون مانيير ان بتي بو تري سامبليفيي. نحاولوا نخليوها فان، نحاولوا نستافدوا مجموعين. جو بونس ايوب صديق تكلف بلا بروميير بارتي سي سا.
يس ما شاء الله نتكلم في البروميير بارتي. دونك السلام عليكم. كما قال استباء انا ايوب، فريشلي انجينير، لا فريش انجينير. يلا البارح تخرجت. دابا انا ستاجير في دايس يوم سي سي بي. المهم دايس انا براسي استباء ما عرفتش دايس واش ستارت اب ولا شركه. واحد البلدين قداش وفين الناس كيخدموا. دونك كنظن انه شي حاجه اكثر من ستارت اب والله اعلم. المهم دابا انا تقريبا في الشهر الاخر ديالي ستاج الحمد لله. دونك without further ado ندوزو نشري معكم slides. Yes, I'm ready to present. Okay. اوكي just a moment. So yes
بريزنت نديرو ديك بريزنت للفوق.
ها كنظن بلي راه كتشوفوا السكرين ديالها.
بريزنت راه كاينه حدا شير كاينه
يس
يا
يس يس كنبغي نديرها ولكن بعض المرات كنبغي نخرج باش كيعجبني نخربق شويه السلايدز بالستيلو ولا شي حاجه. المهم نديرها دابا ومنين نحتاج نخرج راه نخرج.
خذ راحتك كلشي ديالك.
كتبان لكم دابا اتس بيغ انف دابا سكول
وي بشكل
اوكي. دونك كما قال السي يوسف اليوم غادي نتعرفوا شويه على لي باز ديال الديب ليرنين. وملي كنقولوا ديب ليرنين كنقولوا لي ريزو نورون ياك. هذا التوك غادي يكون برعايه السي يوسف مراد وانا ايوب ناصر. غادي نشوفوا بزاف ديال الحوايج هنا ماشي هاد الطابلو د ماتيير ما نديوش عليه كاين بزاف ديال الحوايج اللي ما كاينينش في الطابلو د ماتيير. المهم كاين نشوفوا لي نورون لي بيرسيبترون شنو الفرق بيناتهم شنو هما اصلا. نشوفوا المالتي لاير بيرسيبترون شنو كيفاش كيخدم اون جينيراليزم. ما غاديش ندخلوا في الديتاي ما غاديش ندخلوا في الكالكول ما ندخلوش في داكشي الاخر ويس وكيفاش كيخدم اكزاكتلي. من بعد سيوس غادي يدوز غادي يهضر على الفاندامنتالز ديال الار ان ان ولا الفاندامنتالز ديال لي اركتيكتور ديال الار ان ان اون جينيرال. من بعد غادي يدوي على الترانسفير ليرنين ومن بعد غادي يدوي على الان ال بي. وفي اخر حاجه غادي تكون واحد البريف هضره على الترانسفورمرز حيت من بعد غادي تشوفوهم من بعد مع جينيريتيف اي اي كورسز اللي جايين من بعد ياك السباق.
Okay. Sorry. What is the question, please?
قلت لهم على ترانسفورمرز غادي يكون واحد الانتروداكسيون حيت مازال غادي نشوفوا من بعد مع الجينيريتيف اي اي كورسز اللي جايين من بعد توكس اللي جايين ديال
Yeah, exactly. For example, last episode كنت about machine learning وكانوا يهضروا شويه على deep learning يعني بحال داروا انترو التورك ديالكم يعني انتوما فيل فري تقدروا ديروا الانترو لاب كامين توركس فيل فري.
اكزاكتلي. سو كنبغي نبدا بواحد الهضره ديال واحد السيد اللي كيعجبني بزاف كيفاش كيهضر كيعجبني بزاف كيفاش كيقدم لي فيديو ديالو. ما عرفتش تعرف واحد اليوتيوبر معروف المهم معروف شويه ماشي بزاف المهم معروف سيتو مايكل ستيفنز هو واحد اليوتيوبر اللي كيشد دي كونسيبت وكيحاول يردهم ببساط يعني من واحد من لي كونسيبت اللي كيحاول يردهم ببساط هو هذا الكونسيبت ديال نيورال نيتوركس. في واحد الفيديو ديالو ولا واحد المره ملي كان كيهضر دار واحد الحاجه اللي هي a single microscopic brain cell cannot think and is not conscious but if you bring in a few more brain cells and a few more and connect them all at a certain point the group itself will be able to think and experience emotions and have opinions and personality and know that it exists. شنو كنستافدوا من هنا؟ كنستافدوا انه حتى في الدماغ ديالنا كبنادم الا جينا كان عندنا نيرون واحد ما عنده باش ينفع ما عنده باش يفيد وما غادي يدير حتى حاجه ولكن منين كداك النيرون كنزيدوا ليه بزاف ديال النيرون اخرين كيوليو somehow كيعرفوا يحسبوا كيعرفوا يقراو كيعرفوا يهضروا كيعرفوا راسهم بلي راهم كاينين اكسترا اكسترا. So this is very interesting because it's the same thing when it comes to سمحوا لي نخلط شويه لونجلي مره هو نفس الحاجه ملي كنجيو كنهضروا على الارتيفيشال نيورال نيتوركس. الارتيفيشال نيورال نيتوركس are basically the same حيت حتى هما دي نورون اللي هما مخودين من لي نورون ديالنا يعني كيفاش حنا لي نورون ديالنا دايرين يعني مخودين من تما من نفس الطريقه الخدمه من نفس كلشي وكيكونوا كونيكت بيناتهم. واحد ما عنده ما يدير لك يعني يقدر يدير واحد الكالكول بساط حنا غنشوفوا ولكن ما غاديش يقدر يدير لك شي حاجه اللي هي واعره كما كنعرفوا دابا داكشي اللي كتعرف اي اي كان. اول حاجه خصنا نشوفوها ام سو سوري بعدا على ماي انرجي حيت ام سو تايرد اليوم ات واز سو تايرين نورمالمون ماشي بحال هكا نورمالمون مور انرجيتيك اللي كانوا شاهدين كيعرفوني راه عرفوني بلي مور انرجيتيك ام سو سوري يس. سو ذا فيرست
سي ايوب نسيت ما قلتش ان السي ايوب كان عنده كونفيرونس مع تسعود ولكن اين تسعود واش تسعود ام ولا تسعود بي ام
بجوج
الصباح فوالا بجوج عنده اليوم بجوج مع ام و بي ام سو هو بازي سيغ بن قرير وفاق مع الخمسه مسكين دايو معاه فوالا شد التران ومشى لكازا دار واحد الكونفيرونس ديال جينيراتيف اي موروكو في ليمسيت كازا وعاود شد التران عاوتاني رجع لبن قرير باش يكون معنا توداي سو ثانك يو فيري ماتش ايوب
ودي مرحبا. ايوا قيس. سو وي كيب جوين. قلنا اول حاجه نعرفوها هي شنو هو بيرسبترون. بيرسبترون هو تقدر تقول اول حاجه بريزونطاج كحاجه كنورون ارتيفيسيال. هو a simple model of an artificial neuron introduced by Frank Rosenblatt, I'm sorry, in 1958. So it's really old. هادشي كيبين لنا انه ماشي غير الاي اي اللي really old، حتى النيورال نتوركس هما really old. اوكي. الفانكشن ديالو كانت ايزي، كانت سامبل. شنو كيدير؟ هو كيشد هذوك الويتس ديال هذوك الانبوت كيجمعهم وكي ابليكي عليهم واحد الحاجه سميتها ستيب فانكشن. هاد ستيب فانكشن ماشي بحال الاكتيفيشن فانكشن اللي نشوفوا من بعد ولا غنهضروا عليهم من بعد. اون جينيرال هاد ستيب فانكشن كتخليك الاوتبوت ديالك تردو لك يا 0 يا 1، يعني الاوتبوت كيكون بينار، ما تيكونش كونتينيو. اوكي. سو هاد الكلاسيفاير هذا مجرد لينير كلاسيفاير، يعني كيقدر شنو كتعني لينير كلاسيفاير؟ يعني كيقدر يسيباري لك لي دوني اللي هما لينييرمون سيبارا. يعني الا كانوا عندي واحد لي دوني اللي هما مخلطين ولا شي حاجه بحال هكا، هاد النورون هذا ولا هاد البيرسبترون ما غاديش يقدر يسيباري ليا هذوك لي دوني. باينري اوتبوت كما قلنا انه الاوتبوت ديالو باينري يا 0 يا 1. شنو كاين هذا الشيء؟ يعني الا درنا في كلاسيفيكاسيون غادي نقدر نخدم به على دو كلاس. كاين دي ميثود اللي نقدر نديرو باش نخدم فيه على مالتيبل كلاسز، ولكن كواحد بريسبترون واحد غادي يخدم به دو كلاس، يدير لي سيباراسيون بين دو كلاس. سينجل لاير يعني هو فيه لاير واحد، بريسبترون واحد، ارتيفيشال نورون واحد، وما كاين لا هيدن لايرز، ما كاين حتى شي حاجه. اوف كورس ات نوت سوتبل فور كومبلكس باترنز. يعني كانت عندنا واحد اليوز كيس اللي صعيبه بزاف، هاد اليوز اللي خصها بزاف ديال الكالكوليشنز وبزاف ديال فيها شي فيتشرز معقدين داكشي. اوف كورس ما غاديش يخدم ليه. So how the neurons different ولا how neuron is different. The difference ما بين neuron وما بين perceptron basically في الطريقه ديال الخدمه ديالهم لداخل. اللي هما بجوج بهم تشوفوا من الفوق راه بحال عندنا input، عندنا واحد الكالكول، وعندنا output. اوكي. عندنا واحد activation function وعندنا output، ولكن هنا it's fundamentally different than a perceptron because علاش؟ a basic unit قال لك واحد النيورون هو a basic unit in both biological brains and artificial neural network. ياك function ديالو هو receives input كما قلنا process them via weight sum، يعني هو كيدير السم ديال الويتس. شنو الفرق هنايا؟ الفرق هو انه في النيورون عندنا activation functions اللي هما ماشي step functions، عندنا activation functions اللي كيخليو لي الاوتبوت ديالي يكون ما بين 0 and 1، ماشي غير 0 or 1، تكون ما بين 0 and 1. and this is very important. اوكي. علاش very important؟ حيت هنا كنجي كنخدم هذوك ندوي عليهم دابا باش نحيدوهم علينا. ملي كنجي كنخدم هاد الاكتيفيشن فانكشنز تاع ريليو سيغمويد ولا تاع اتش، هادو شنو كيديروا ليا؟ they represent ولا they inject non-linearity into the model. يعني كيردوا لي الموديل ادابتي لي دوني اللي هما نون لينيير. اوكي. سو هذا هو الهدف ديالو الاكتيفيشن فانكشنز. المين جول ديال الاكتيفيشن فانكشنز هما كيردوا لي الموديل ديالي ادابتي لي داتا لي دوني اللي هما نون لينيير. اوكي. كما قلنا هنا can be non-linear, uses activation functions like ReLU, sigmoid, 10H, etc. Part of complex architecture used in deep learning like CNN. اوكي. هذا النورون هذا النورون العادي اللي دوينا عليه دابا هو اللي كتخدم ليا في CNN ولا كتخدم في RNN etc. Transformers of course. Continuous output كما قلت، يعني الاوتبوت تكون ما بين 0 and 1 ماشي 0 or 1. Flexible, supports multiple layers and deeper structure with backpropagation and optimization. حنا دابا نهضروا على كيفاش كيتعلم من بعد. Okay, so now we reach the point غنهضروا على المالتي لاير بيرسبترون. علاش كنسميوه مالتي لاير بيرسبترون وماشي مالتي لاير نيورون؟ ما عرفتش ولكن كيسميوه مالتي لاير بيرسبترون، ولكن بيسيكلي هذا هو الاي ان ان. اوكي. artificial neural network. ببساطه شنو هي artificial neural network؟ It's a machine learning model designed to mimic the functions of structure of the human brain. ببساطه ان واحد لي نورون ياك وعندي ديك لي نورون ريبريزونتي في واحد لي كوش، وهذاك لي نورون انتركونيكتي بيناتهم ملاصقين بيناتهم، وهذاك هذاك كل نورون ملاصق مع واحد نورون بواحد الويت. يعني كل نورون نقدروا نقولوا داك الويت هو الاهميه ديال هذاك النورون بالنسبه للنورون اللي من بعد منه. It's not the most perfect definition ولكن just understand it as this for now. ANNs are composed of multiple nodes which imitate biological neurons of the human brain. The nodes take input data and perform simple operations on the data. يعني قلنا كيشد هذاك الانبوت كي multiply by the weights كيجمع داك الشيء plus the bias. We're going to see that each link between two nodes is associated with weights. Yes, nodes are arranged in multi-layer, etc., etc. So this is what an ANN looks like, or this we can call this fully connected neural network. شنو fully connected؟ شنو الفرق ديال fully connected وما بين ماشي fully connected؟ fully connected هو اي نورون مكونيكتي مع لي نورون الاخرين، اوكي، يعني نورون كاملين مكونيكتي مع بعضياتهم. ماشي فولي كونيكتد يعني لي نورون يقدر يكون مثلا هذا مكونيكتي مع هذا وهذا، هذا مع هذا وهذا اكسترا، يعني ماشي فولي كونيكتد. سو هنا غادي نحاول ندوي واحد شويه وغادي نخرج حيت هنا خصني نخربق شويه. هوب تكونوا كتشوفوا انا ندير لكم الشويه بحال هكا على هذه. اوكي كتكتب هنايا. اوكي سو نفترضوا ياك انه هاد الANN هاد الارتفيشال نيورال نيتورك ولا هاد الMLP is trained on detecting مربع ولا ماشي detecting let's say recognizing ولا classifying ما بين مربع مثلث and دائرة. اوكي سو الانبوت هادو هما هاد البيكسلز هادو كاملين ديال هاد المربع البيكسلز ديال المثلث والصنف. let's say ان دابا عطيتو انايا مربع. سو فوكس وذ مي مزيان في هاد السلايد هذا حيت غادي نحاول نشرح فيه تقريبا كلشي حيت ما كاينش طريقه اخرى. الا بغيت كنوريكم الكتابه ما غاديش تعقلوا عليها. سو نفترضوا ان دابا ويفيديت مربع هذا تريند يعني تريند اوكي تريند ولكن بغيت نردو انا احسن ولا ليت سي انه عمري ما ترينيتو. اوكي صافي هذا جديد ما ترينيتوش. سو وي ستارت جيفين ات هاد المربع هذا صافي كما قلت لك هادو البيكسلز ديالو طن 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 صافي كيدخل لنا هذا اللاير هذا الثاني هذا كذا. هنا في الاوتبوت هنا عندي دو كلاس داكشي علاش نحيد وحده نحيدو دائره. اوكي عندي مربع مثلث هنايا مثلا خرجت لي 0.0 خرجت لي 0.7 مثلث. اوكي 0.3 سوري 0.3 مربع. واش هادشي مزيان؟ واش هاد الموديل ديالي تعلم؟ المهم يقدر يجاوبني شي واحد ماشي مشكل.
الشباب قال لك نو، محمد قال لك نو ما تعرفش بام قالت لك نو.
اوكي سو بيرفكت سو الموديل ديالي هنا ما تعلمش اوف كورس ما تعلمش حيت مازال يلاه بدينا ترينين. نورمالمون راه كيكونوا لي ريزولطا كيفاش من هادو ما حنا دابا جاست فور اندرستاندين. هنا الموديل ديالي يلاه كيتعلم دونك هنايا اوف كورس غادي يعطيني واحد الريزولطا اللي خايبه مره في مليون مره مع شي حاجه شي بروبابيلتي صغيره بزاف من اول مره غادي تصدق ولكن it's not always the case. لما الكيس اللي هي كاينه ولا هي ديما كاينه هو انه ما يمكنش في الاول الموديل ديالي يعطيني واحد الحاجه اللي هي مزيانه. دونك شنو كيطرا هنايا نجي معكم لهنا. هنايا هاد لابارتي اللي شرحت لكم دابا هاد لابارتي دابا الداتا كتمشي بحالك فهمتي كتمشي دخلت انا دخلت هذوك لي بيكسل اللي هما هادو مع الويتس ديالهم، ياك الويتس ديالهم كاينين هنايا، هادو الويتس اي حاجه عندها علاقه بالويتس، هنا ويتس نفس الحاجه. هاد الداتا هادي كتمشي في هذا الاتجاه. اوكي، هادي شو كنسميوها الفورورد بروباغيشن. هذه هي الفورورد بروباغيشن، يعني الداتا ديالي كتمشي من الانبوت حتى الاوتبوت. هنا شنو عندي؟ الى عقلتوا قلنا انه اي نورون شنو عنده ويت، ياك، وعنده بايس، وعنده اكتيفيشن فانكشن. هنايا نورمالمون كتكون سيغمويد. اوكي، اكتيفيشن فانكشن ديالنا هي السيغمويد، هنايا السيغمويد. هنا في اخر لاير اللي غيعطيني فيه هاد لي بريديكسيون هادو، يعني الاوتبوت لاير، ما كنديرش السيغمويد، كندير واحد الاكتيفيشن فانكشن سميتها سوفت ماكس. هاد السوفت ماكس هادي الهدف ديالها هو انها تشد هاد الريزولت اللي يخرج ليا من هاد اخر لاير ولا من هاد اللايرز كاملين، طبعا حيت هادو كلهم الريزولت عندها علاقه بهذا الشيء كامل. هاد الريزولت اللي خرجت هنايا كتشدها وكتحولها ليا دي بروبابيليتي. اوكي، دي بروبابيليتي بحال اللي كتبت لكم هنا، يعني 0.7 هي البروبابيليتي انه داكشي اللي وريتيه في الاول مثلث، و0.3 هي البروبابيليتي انه مربع. سو ذس هاد البروسيس هادي كتسمى الفورورد بروباغيشن. واش بالفورورد بروباغيشن كافيه بوحدها باش يتعلم الموديل ديالي؟ كيفاش غادي يعرف هاد الموديل ديالي اصلا شنو غادي يدير هنا؟ ولا كيفاش غيعرف اصلا باللي خصو بلي هذا اصلا واش مثلث ولا مربع، ولا خصو يولي 0.9 مثلث ولا 0.، ما عندوش كيفاش يدير يعرف. داكشي علاش we have واحد الحاجه سميتها الباكورد بروباغيشن. شنو هي الباكورد بروباغيشن؟ اون جينيرال باكورد بروباغيشن هي باش كيتعلم لي الموديل ديالي، هي الميثود اللي كتعلم بها الموديل. واحد الموديل ديال الارتيفيشال نيورال نيتورك كما بغى يكون سي ان ان ار ان ان ام ال بي عادي، كيتعلم ليا عن طريق الباكورد بروباغيشن. يعني كيجي كما قلنا ها هما لي دوني، ياك، الويتس ديالهم كيطرا لهم لا سوماسيون، يعني كدير شنو كنديروا هنايا نورمالمون كنديروا x multiplied by the weight. okay, so plus the bias normalement plus the bias. هنا just for simplicity ما كنزيدوش البايس. اوكي، just for simplicity، يعني وهنا كنديروا لا سوم ديال x xi وهنا من i of course من i equals 0 حتى n، وهنا 4 في الحال. اوكي، سو كنديروا هاد السوماسيون، هاد المالتيبليكيشن، وهاد كنديروا السوماسيون ديال هادشي كامل، ومن بعد كندوزوه الاكتيفيشن فانكشن. ملي كندوزوه الاكتيفيشن فانكشن كيعطينا واحد الريزولت، واحد الاوتبوت، ياك. مثلا في الحاله ديالنا اللي قبل واحد البريديكسيون ديال شحال هي البوسيبيليتي ولا البروبابيليتي ديال انه يكون مثلث، شحال البروبابيليتي انه يكون مربع. شنو كندير انا بهاد البروبابيليتيز هادو؟ هاد البروبابيليتيز هادو هما اللي كيعاونوني انني ملي كنحاول كنحسب الايرور. اسهل طريقه باش نحسب الايرور هي المين سكوير ايرور. اوكي، المين سكوير ايرور هي اسهل طريقه باش نحسب الايرور. شنو هي المين سكوير ايرور ببساطه؟ هو كنحسب لا ديفيرونس اونتر شنو متوقع خاص يخرج ليا، يعني حيت هنا راه انا في سوبرفايزد ليرنين. اوكي، this is a supervised machine learning algorithm. ال ان ولا سي ان ولا اي موديل ديال الارتيفيشال نيورال نيتورك راه سوبرفايزد. المهم ماشي اي موديل، ولكن حنا كنهضروا على هادو دابا اللي كندويو عليهم is a supervised machine learning algorithm. اوكي، يعني هنايا راه عندي باللي مثلث كتساوي 0 مثلا، ياك، وعندي باللي مربع كتساوي يعني الموديل ديالي راه عارف عنده لي ريبونس. اوكي، يعني عنده لي ريبونس، عنده الداتا ليبلد. اوكي، عنده الداتا ليبلد. داكشي علاش شنو كيجي هنايا، كيجي وتيقارن ليا شنو خص يكون مع شنو خرج ليه. دابا هنايا الايرور شنو هو؟ الايرور هو 0.7. اوكي، الايرور هو 0.7. هذاك الايرور with something we call the gradient descent, which is هاد الميثود باش كنحاولوا نمينيميزيو ليغور. I will explain it fast حيت it's really mathematically شويه complicated. ولكن I will just try to explain it المهم قبلوا عليا. So I want you to imagine أن هذا هو الموديل ديالي مثلا، هذا هو الفونكسيون ديغور ديالي ياك، وانا بغيت نمينيميزيها. الا بغيت نمينيميزيها فين خصني نوصل هنايا. اوكي خصني نوصل هنا. سو هذا الجريدينت ديسنت ببساطه هو واحد الطريقه اللي كتخليني نبدا في واحد البلاصه اربيترير، واحد البلاصه اني فهمتي اعتباطيا، مثلا نقولوا ان بديت هنايا ياك، وكيخصني نمشي طريقه كيفاش نوصل للمينيمم. الطريقه باش نوصل للمينيمم الجريدينت ديسنت هو ببساطه هو الكالكول ديال الديريف ديال دي ديريف. يعني كنبقى ندير نكالكولي دي ديريفي نكالكولي دي ديريفي نكالكولي لي ديريفي طن 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 حتى كيولي لي الديريفي هنايا، حتى كنوصل حتى كنلقى راسي وصلت لهنا. بغيتكم كيفاش ايماجينيوها ككره كتهبط. يعني حطيتي كره في واحد البلاصه، حطيتي واحد الكره في واحد الزلافه، حطيتها الفوق تهبط لتحت، تهبط تلقى المينيمم. يعني المينيمم هو القاع. المشكل فين كاين هنا؟ المشكل فين كاين في هذا الكا هذا؟ المشكل هو الا كان عندي لي جو باك، الا كان عندي شي حاجه بحال هكذا مثلا، بحال هكذا بحال اوكي بحال هكذا. هنا فين هو الجلوبال مينيمم؟ الجلوبال مينيمم هو هذا. ولكن سيبوزون انه هذاك حيت قلنا في الاول راه كتبدا اربيترير. تخيل معايا ان جيت هنايا، ان حطينا تما يعني البوين دو ديبار ديالنا هي هاد البلاصه. فين هو راه الجريدينت ديسنت كتلقى شي مينيمم كتحبس، ما كتقلبش على احسن مينيمم، كتلقى شي مينيمم كتحبس، كتقول لك انا صافي. فين هو اول مينيمم؟ هو هذا. ملي غتلقى هذا المينيمم هذا غتحبس، وتشيز ماشي خايبه من واحد الناحيه، راه ماشي خايبه. نقول لكم علاش. طبعا لي فونكسيون ديال بحال هاد الحالات هادو تكون معقدين بزاف على هكذا، ولكن هذا غير اكزومبل. يقدروا يكونوا بزاف ديال لي مينيمون، يقدروا يكونوا بزاف ديال التخربيق يعني قديم مرونه بزاف. هذا غير اكزومبل. علاش زوينه؟ علاش مزيانه؟ حيت الا جات هنايا هذا راه الجلوبال مينيمم. عرفت شنو كيعني الجلوبال مينيمم؟ يعني ان الموديل ديالي صافي ما بقاش كيدير غلط، ما بقاش كيغلط في مره، ما بقاش كيغلط، وصافي فيت على الداتا 100%. شنو كتعني فيت على الداتا 100%؟ كتعني اوفر فيتين. اوكي سو وي هاف ا بيج تشانس ان نطيحوا في اوفر فيتين الى لقينا المينيموم جلوبال. المهم ما تحمقوش راسكم بهذا الشيء. البلان اللي بغيت نشرح لكم هو انه كيطرا واحد الايرور كالكوليشن، موراها كيطرا واحد الكالكول ديال هاد الجريدينت ديسنت. من بعد كتخرج لنا كنديروا واحد الحاجه كسميتها تشين رول هي باش كنبقاو نحسبوا حتى كنوصلوا لهاد الويت هادو اللي هنايا. هاد الويت هذا اللي هنا مثلا نسميو هذا ويت 10 واقيلا مثلا، فهمتي؟ ويت 10 كنوصل هاد الويت 10 هذا من شحال هذه مثلا كان هاد الويت 10 5 ولا 0.5. اوكي كان 0.5. انا جيت حسبت الايرور وحسبت التخربيق كامل وجيت لقيت بان هاد الايرور هاد الويت هذا خصو يتبدل، خصو ما يبقاش 0.5، خصو يولي مثلا 0. ما كنعرفش نكتب 0.2. اوكي سو هاد الويت القديم مشى، ولا عندي ويت جديد ديال هاد الاتش ديال هاد النيورون هذا اللي في هاد الاتش ان ولا اللي نسميوه الاتش 3 مثلا في الهيدن لاير نمبر 3. عندي واحد الويت جديد ديال هاد النيورون هذا. اوف كورس نفس الحاجه كطرى على هذا، كطرى على هادشي كامل، وغادي عاوتاني بحال هكا. هذه كتسمى شنو كتسمى؟ الا كانت هذه فورورد بروباغيشن هذه كتسمى باك بروباغيشن. كمان جايز وفقوا معنا، انا عيان كنجاوب راسي. جاوبونا شويه، تحركوا شويه باش تشجعوني انا.
سميتها البرهان بالترشح اختي.
exactement quel que soit n appartient à n. ياك اوكي دونك هنايا شفنا الفورورد بروباغيشن. اذا الفورورد بروباغيشن هي منين كنفيد الموديل ديالي واحد بحال الاكزامبل واحد المربع كيمشي هذاك الداتا ديالي كتمشي فورورد حتى كتسنى واحد الاوتبوت. كنشوف داك الاوتبوت كنكالكولي ليغور. يعني هنايا قلنا كنكالكوليو ليغور، يعني كنديروا الفونكسيون ديغور نسميوها مثلا. قداش ما علينا. كنكالكليو هاد ليغور، من بعد ملي كنكالكليو ليغور كنديرو اللعيبه ديالنا اللي كنا كنهضروا عليها، داكشي الماط المعقد اللي ما فاهمينوش مزيان. ومن بعد كنجيو وكنديرو الابديت ديال الويتس. صافي الابديت ديال الويتس كيبقاو غاديين كتابديت الويتس كاملين. عاوتاني كندوز هذا المربع، عاوتاني كنلقى واحد الليرور جديد، عاوتاني كنبقى ندير نعاود هذه غادي وكتوبتيميزا ليغور ديالي غادي وكيتوبتيميزا اوف كورس، حيت هذه اللي كتحاول توبتيميزي غادي كنقص. وهنا كنشوف نقدر نقول واحد الحاجه كتسمى الليرنين ريت. هي شحال الموديل ديالي كيتعلم. اوكي، يعني شحال الموديل ديالي كيزيد لقدام. هذه هي واحد لانفورماسيون زوينه تقدر تجبدها من هاد الايغور والجريدينت ديسنت. صافي هاد كيبقى غادي بحال هكذا فورورد باكورد حتى الموديل ديالي كيكونفيرجي، وكنكون انا راضي على الموديل ديالي. صافي هاد الموديل ديالي خدام الحمد لله. اوكي، هوبفلي هاد شويه مفهوم. انا نشوف الشاط دغيا. اوكي التصفيقات يعني صافي فهمتوا. ولكن هاد الشيء هذا راه تشوفوه من بعد ما تفهموا فيه حتى شي حاجه. هذا المين سكواد ايرور كيكون عندي ملي كيكون عندي كلاس وحده، ولا كيكون عندي مثلا ريغريسيون. اوكي، كندير هذا المين سكواد ايرور. شكون عندي ريغريسيون كندير مين سكواد ايرور. بحال ما كان عندي في هذه الحاله هذه جوج ديال الكلاس. هنا راه كاين بزاف ديال الكلاس، مي نقولوا حنا جوج ديال الكلاس، نعتبرهم جوج ديال الكلاس. كنديروا اللي قال السباق هي الباينري كروس انتروبي. الباينري كروس انتروبي هي واحد الكالكول داير، واحد الفانكشن ديال الكالكولير. ما عرفتش واش بغيت نوريها لكم ولا ما كنظنش مهمه صراحه. تقدروا تقلبوا عليها، سي فونكسيون ما عمرك تخدموها في الكود. تعيط ليها في تنسرفلو ولا تعيط ليها في بايتورش ولا ايفر داكشي اللي كتخدم به. المهم اللي خصك تعرف هو انك تخدم اللي يكون عندك دو كلاس. هذا الباينري كلاس انتربري اللي كتخدم اللي يكون عندنا دو كلاس. اللي يكون عندنا اكثر من دو كلاس كنخدموا الكاتيجوريكال كروس انتربري. جاوبتك السباق؟ انا عارفك عارف الجواب وقاعد تطلع عليه.
يس ثانك يو فيري ماتش. انا ما سمعتش الجواب، راه فاح القهوه الصداع ياسر. ثانك يو ايوب، ميرسي بيان. انا تنشوف غير الشات. ثانكس. باي ذا واي فيل فري تهضر باش ما بغيتي Arabic, French, English, feel free اضرب. ثانكس.
I think we have someone who only understands English.
Yeah, we
They
have
said English, please.
yeah, we have actually two guests
Okay.
from Arizona, right, Robert?
Yes, I'm from the USA, baby. Trying to get some information, see what's going on in Morocco, baby. Let's rock and roll.
Okay. Love the energy. Okay, love the energy. Yes. What do you want me to do, Robert? Do you want me to repeat?
Yeah,
No.
which part needs some clarification for you?
Yes.
No, I just wanted to know more or less the algorithms, the ones that you're using right now, in regards to hyper optimization. in regards to, I don't know exactly to what extent you use. Do you guys use? Oh God, Uzair, what's the name of that one? I'm trying to remember. What's the one that we use? Oh God, trying to
Epsilon.
remember the name.
Find the optimal parameters.
Yes.
Grid search.
Yeah, because we're having problem with gradient decay,
Oh yes.
and that's
Well,
the
there are some other methods like heuristic methods.
Optuna. Yeah, in Optuna, we use
Optuna.
Optuna to do hyperparameterization and optimization. So I was just wondering whether you have had any issues with that as well, in regards to you having an algorithm, and then inside, because Optuna does a hyper and optimization as well, right? But I don't know if there's a conflict. We're having problems in regards to there being restrictions. I don't know if you've ever experienced that.
I don't think so. I've never went that far, to be
So,
honest. Maybe Yusuf can help.
yeah, so I never used Optuna, to be honest. Okay.
Yeah, me too.
But for the hyperparameter optimizations, it depends on the context. Okay. So what's actually the type? This is a general knowledge about how the neural networks work. Okay. And there are like many types of neural networks. We'll cover some of them, like the RNN and LSTM, in the upcoming slides. But in your context, which type are you using? So we know which hyperparameters optimization problem are you facing exactly.
I'm just having Uzair get that insights to you.
Hajam said there is greedy and a star. Like greedy, you mean like in reinforcement learning? A star, it's like an algorithm to find the optimal.
Yeah, epsilon, greedy epsilon, right?
No, I think epsilon greedy is it's a reinforcement learning algorithm. Well, it's not. It's
Yeah.
it's a concept.
Like, sorry, Ayub. What's actually the context? Is it on reinforcement learning? Is it on some classification task? Is it for images, for sound? Any additional infos will help us like give you a deeper insight about that.
Yeah, for model parameters.
Yes. So I would just ask you, Robert, if it's okay with you. We can maybe discuss this,
Yes,
me, you, and
thinking.
Yusuf. Yeah, and
yes.
because this is supposed to be
no,
like
I get it.
a
No, I get
beginner,
it.
a beginner friendly.
I agree. I don't want to take over. I agree. I'll let Yosef continue, and then we can talk after. I don't want to take over the. I agree. Thank you.
No problem. Yeah, but you can ask any questions during the session. Yeah. So going back, so we said that first we go by the forward propagation, then we calculate the error, do the gradient descent, go back and calculate do the calculations for the backward propagation, update the weights, and do it again and again and again. So what's next? Let me go back again to full screen. Yes. So what are the problems with simple MLP? So simple MLP, you need to remember that it is simple. Okay, it does not extract features. It does not do something complex. One problem with it is with high dimensionality. For example, if we have images, MLP tend to suffer when it comes to 3D image, not 3D, but RGB images, because RGB images have like 3 types of colors, like red, green, and
red, green, blue, and this for the digital images. And we have the printing images. It's CMY, something like that. Say CMYK. It's cyan, magenta, yellow, and K. The K is the black, yeah, like the alpha, yeah.
Yes.
We have 2 systems of colors.
Yes. Also, there's like the I forgot the name, but no problem. This is just to make you to put you into context. high dimensionality means, like, for example, I said images with the 3 colors, for example, the RGB system. When we have that type of data, MLP suffers in training and gives bad results. The second problem is translation invariance. What does it mean with translation invariance? In MLP, for example, if I go back again to to not so full screen, for example, if I have this is like 7, okay, this is 7, and this is what? This is also 7, okay. 4.
7 up, yeah.
Yeah, so for NLP, for MLP, I'm sorry, for the MLP, for simple MLP, these are not the same number. Somehow these are not the same number. Or let's say not even this one. Let's say just this. Okay, it's a little bit shifted, for example, to the right in the image, or a little bit shifted down, or a little bit shifted up. So MLP does not learn the shape of the thing it's learning. So this is a big problem. It makes training very hard, and it gives, of course, bad results. Overfitting risk, large parameter space. When we have a lot of parameters, our models tend to overfit, which is a big problem with MLP or multi-layer perceptrons. So as I was saying, for example, I have this image of an elephant that has 224 by 224 pixels. Imagine 224 by 224 means that every pixel is represented by a neuron. That I need you to understand this very, very much. Every pixel is represented by a neuron in the input layer. So if we have 2024 by 2024, meaning that I need to multiply those numbers, and I will get how many neurons I have in my input layer. For example, here I have 150 million point 528. I'm sorry, I'm mistaken somewhere. 150,528. It's a big number. It's a big number. Okay, so we have a lot of input neurons, and I need to give every one of them a weight. Okay, I need to give every one of them a weight, because this is how MLP works. So moving on from the first layer, which is input layer, to the hidden layer, we're going to be jumping from 19. Oh, sorry, this is millions. 19 millions 267 something weights to 2.4 billion weights. Can you imagine? This is big. This is very big, and it's going to make training really, really hard on the model. Not talking about if we move to the third hidden layer, it's going to be like 300 billion. It's very, very hard. So here where it comes the utility of CNN in working with high dimensionality data like images. This is why you heard sometime that if you are working with images, you have to work with CNN, because CNN is the best with images. Why it is the best with images? We're going to see some examples on why, because if we go deep, we're not going to finish today. It's a big course, CNN. But I'm going to just mention some stuff. So parameter sharing. Parameter sharing is something that makes CNN better and much more optimized than simple MLP. For example, in a simple MLP, we said that we're going to make every pixel as a neuron, and every neuron has a weight. Okay, but with the CNN, we'll have something good, and something that will optimize this part of the input. At least if we optimize the input, obviously the other layers are going to be optimized too. So for example, I want you to look here. Let's say this is a pixel. Of course, this is a lot of pixels, but let's say this is a pixel, and this is also a pixel. Can you compare between them? What do you see? You see that this pixel has practically the same information as this pixel when it comes to, for example, here we are just working with colors, let's say. Okay, the same color, so it's the same information. Why would I give this pixel a weight and give this pixel a different weight? Okay, so parameter sharing is when I have similarities or the same pixels, I give them the same weight, and this will allow our CNN to be much more optimized. I hope you understood the parameter sharing. I want you to go and look it up and understand it better, okay? Because it's really, yes, question?
Yes, Ayub. About the similarity, do you mean the position, the place of the pixels, or the code color for the same pixels?
For example, we are going to say it's the color for this example, but we don't know what our architecture is learning. Is it learning shapes or is it learning colors? But we say that just for simplicity, for making you understand the parameter sharing, I suppose that the color is the learning, the parameter that is learned. Okay, it's the thing that we're learning, but it can be different. It can be like the shape. It can be the edge or something like that. But let's say it's color. Okay, just for simplicity.
Yeah, thank you.
Okay. But if I made a mistake, you can flag it out. I have no problem. I'm learning. I'm learning with you guys. So if you feel something that said something wrong or anything, you can just flag it out. No problem. Hopefully, I'm not giving you bad information. No, I'm not giving you bad information. So yeah, moving on to translation invariance. So in the contrary of MLP, in CNN doesn't care about the position of the shape because it learns the shape. So it tries to learn the shape however it is, tilted, shifted, it doesn't care. So it's a good thing about CNN because basically in CNN we're going to see why it does that, because CNN extract the features from the images. So for CNN, images are features, so it doesn't care about where the feature is, basically. Efficient training, we said that it reduced the numbers of parameters with the parameter sharing. As I said, in parameter sharing is much complex. It's a much more complex concept that I explained to you. I just wanted to give you an overview. I urge you to go and look it up because it's really interesting. Yes, so this is because we already spent 45 minutes in this. Yeah, so this is an example of an architecture of an architecture of CNN. For example, it is called VGG16. In VGG16 we have input layer, we have the hidden layers, etc., and output layer. Here we can see that our CNN has two main parts. The first part, which is again, I'm going to go like this, which is this part. Okay, this part is the feature extraction part. Okay, this part where our model, our CNN, extract the features from the image, and this part is the prediction part. This part is the part that predicts the output. For example, here a cat, it will predict a cat or or be wrong, predicts a dog, and also we have backpropagation, etc. The same thing as we explained in the MLP. It's the same thing going to happen here. So as I said, we have two main parts. The first part is the feature extraction part, and the second part is the prediction part. Let's now look some very important stuff in here. For example, the convolution parts. This is like convolution layers. It's also something that I need to explain, but yeah, it's going to give it an overview. Okay. A convolution is a kernel, a slide window that goes slides over the image, do some calculations that comes, and will give us this matrix, and we call it the convolution matrix. We call it also a feature map. This feature map, to make the training more efficient, we do something called max pooling. Max pooling is reducing the size of this big matrix. Basically, we do again another sliding window. This sliding window, instead of doing convolution calculations, we just take the highest. For example, when we do max pooling, we take the highest the highest value and keep it. We go again, we slide, take the highest value, keep it, go again and again until we reduce the calculations. We do again the same thing. We do again, we do the convolution on the max pooling layer. We do it again, max pooling. We go until we finally reach the part where it is just a 1 by 1 array. And this 1 by 1 array is the array or the vector that has all the information that was in here. Can you imagine that? It has all the information that's in here. Okay, so for our model, this is an image of a cat. For our model, this 1 by 1 array or the 1 by 1 vector is an image of a cat. So this is very, very interesting. Then we get the prediction. Is it clear? Is it clear?
Yes, thank you, Ayub.
We go to you, Yusuf, or we do the technical part?
As you like. If you wanna like break the rhythm and do some workshop, we can actually start with the workshop of the CNN before moving on to the next topics. Whatever you like, you have the decision.
Okay. It's a simple workshop. It's not very complicated. Just an emotion detection. Something. It's the most basic workshops that you will find when you are working on CNN. Yes. Let me just change
We're gonna
the.
use
Yes.
we're gonna use YOLO for that.
YOLO is after with transfer learning. This is just with
Okay.
CNN.
Okay.
This is
Okay.
this is a direct usage of the CNNs in real life. So we'll try to actually code or like design some CNN architecture that will serve us like to classify, right? To classify the emotions inside some comments.
Yes. So for time
Is it-
It's okay. It's okay.
purposes,
not,
for
It's
time
not
it's
the,
okay.
for time purposes, we are going
It's
to.
okay.
I'm not going to. Yes.
The dog and the cat.
Uh, no. It's on the FAIR 2013. It's a database of human emotions, facial
Okay.
emotions.
know if you're sad or happy.
Yes. So I'm not going to rerun the cells because I already ran the cells. First of all, we need to install the required libraries. For example, TensorFlow, Keras. TensorFlow is the library for everything related to machine learning and deep learning. It has the functions that we're going to work with. Keras is basically the same thing. It's machine learning, deep learning related. Matplotlib is to show our results or to show our data, to plot it. And OpenCV is for computer vision related tasks. Pandas is really known. I think in the first session you have introduced Pandas. It's just to work with our data set. Scikit-learn is for calculations. I think Seaborn is also for it's like Matplotlib. It's for visualization. Here we just import the libraries. Then we load the dataset. Dataset is on Kaggle, so it's really easy to load. We show the head of the dataset. Have here like 0, 1, the head of the Dutch head. You know that Dutch head shows that the first 5 rows. We see here that we have the pixels. This is the pixels of the image, and we have the usage. It's used for training, and the others are used for testing. Here we're just going to check for missing values. This is just for showing the best practices when you're working with dataset. I know that this dataset is clean and it doesn't have any any null values or something, but it's just the best practices for pre-processing. I can see that it's all clear. Then I'm going to this data set information, see how many emotions I have, how many pixels, emotion rows, how many pixels, how many usage. That's the same, because I have no null data. Then I'm going to visualize the emotion distribution using multiple. Here, the emotion count, we calculate how many emotions in each emotion, how many how many lines. We can say how many lines in each emotion. We can see here that we have under representation of disgust, and we have an over representation of happy emotions, which is bad. It's not our topic today, but جابش الوقت, which is very bad. It means that our model is not going to be very good when it comes to disgust, and it's going to be very good when it comes to happy, and it will confuse other emotions with happy, because it has a lot of data in relation with happy. So the model will make more predictions as happy, which is bad. What we need to do is we need to equilibrate the data, to balance the data. To balance the data, we need to balance the data, but we're not going to do it now. Maybe when I send you the notebook, you can do some research on balancing data. We have a lot of algorithms to balance data. You can check them, like oversampling, undersampling, stuff like that. You can balance your data and see if it's better in results. Here I'm going to visualize some samples, some samples from the data set. For example, this is disgust, this is fear, this is happy, this is neutral, surprise, and sad. These are the 7 emotions we have. Some other pre-processing, it's not really important. We just make we stack everything into a NumPy array, so it's easier in training. We do one-hot encoding. One-hot encoding means that here I have seven emotions. So in one-hot encoding is when I take. I will go back to the presentation, I think, because I can't write here. If you want me to explain one-hot encoding, if you don't want to, we can move on quickly.
I think we can move faster because we still have so much
yes,
so much topics to cover. But yeah.
Anyways, one-hot encoding is given 1 in the place of a class. For example, happy is 10000. Disgust is 01000. Angry is 001000, etc. You understood? This is what we are doing here. We are doing some data augmentation. It's also just for best practices. We don't need it in this case. We have enough data. Here we are building our CNN model. So our CNN model needs to be needs to have what? An input layer, hidden layers, and an output layer. So we have an input layer shaped is 48 by 48 because our images are 48 by 48. The first convolution is it has 32 neurons. The kernel is 3 by 3, and activation function is Relio. The second convolution, we do max pooling by a kernel of 2 by 2. Then we do a convolution, a second hidden layer with 64 neurons. Then activation function stays Relo. Then we go to the max pooling again. We flatten. So we take the matrix we saw before, and we make it into a one array. It's a one vector, okay, 1 by 1 vector or 1 by 1 array. Finally, we have the dense layer. Dense layer is the final layer, is the output layer, and we have seven classes. So yeah, softmax, as I said before, softmax is the final activation function when we want to make the predictions. Here we have something called dropout. Dropout is a method to help with the fitting. Let's not go there. Here we compile our model. We train our model with this code. I will send you the code anyway. We finish training the model. We save the model. We plot the validation matrix. We can see here that our loss is what's more important is loss is the loss. We see the training and validation loss are really close to each other. So it means that our model did not overfit. If the training loss and were very apart, it means that our model had overfitted on the training data. But it's fine for now. Evaluations, we see some precision and some F1 score. I will always like advise you to look at the precision and look at the F1 score, because precision alone, it can be very misleading. For example, let's see here, discussed. Have I'm sorry, there is a problem here, or surprise, surprise. Sorry. 64 angry 44. No. So it's good. It's good. So I need to look at the precision and the F1 score. If they are close, meaning that our model is good. If they are if the precision is high and the F1 score is really low, it means that the model is not good. It's just the precision is just lying to us. Okay, this is the confusion matrix. And these are some tests. We tested it on some images from the test data set. Here we have like happy. This one is classified. Thank you. Misclassified again and misclassified again and misclassified again. It's not a very good model, obviously. Predict emotion from an RGB. Here, if you want to predict emotions from an RGB image, in our case, working with MLP, MLP does not accept an RGB image. So we need to convert RGB image to a grayscale image that is a one layer image. It's not with three colors. It's just one color, white to black. And we do this, and it's bad again. We do another thing. Here it's bad because it does not detect the face correctly. We add another thing, which is a model that detects the face to make it better. So here, when we detect just the face and run the model on just the face, it gives the right prediction. So this was the project, the practical project. Thank you so much, guys. I think I give the floor to Yusuf for now. Sorry, I took too much time. So
Yeah,
sorry.
no worries. That was very fun, and that was very instructive. Yeah, great work. Yeah, so the next phase, can I share my screen instead, Ayub? Thank you. Present full screen. Can you see my screen? Right. Okay, so the next topic in our today's day is understanding the sequential data. So we will have an introduction into the RNNs and the LSTMs architectures. Okay, so from what Ayub said in the past hour, imagine we have some inputs that are actually related with each other in some order. Okay, let's say we want to predict the weather. Okay, so the weather of tomorrow depends on the weather today and the weather yesterday and maybe the weather of the last year, etc. Okay, with the MLP, with the traditional neural networks, that fails because it only remembers the inputs that you give it. But that's why actually we did introduce the RNNs and the LSTMs and many of the sequential data supported models. So what is a sequential data first? Okay, so it's a data where the order is critical. It contains some important information that is lost if the order is changed. Let's pick an example. Let's pick an example, a very simple example, where we have this data, this sentence: a dog chasing a cat. This is a very instructive or a very direct sentence that every word depends on the one before and even the one after. Okay, if we change the order as the input, like the cat chasing a dog A, that changes the entire meaning of it. We have many types of the sequence data, like in the speech recognition. So when you're having some spectrogram or some when you're having some spectrogram that the frequencies and everything like it's very related to each other. Music generation, the sentiment classification. When we are doing some sentiment classification on text, on the text, not on the no, on the faces. So we have actually the entire sentence where every word is related to the one next to it or the one before it, or maybe both of them. If we're doing if we're doing the bidirectional, we have the DNA sequence analysis, machine translation, video activity recognition, and name integer recognition. So what is the RNN, the recurrent neural networks? Okay, the problem. So so it's actually unlike the standard neural networks that treat every input independently. So the RNNs are just designed to specifically for a data where the text or time series matches. Okay, their key feature, as we see in this diagram, is a form of memory. So we are introducing something that we call a component that we call a memory. It allows the information from the previous steps to influence the current one. Okay, so let's see how this works over two time steps. So when we have like actually two time steps, like it's very shown here in the graph. So we have the state one and the state two. So in the middle we have the green nodes. Those green nodes are what we call the hidden layers. The hidden layers is where the network performs its calculations. So in those green nodes, it's like there we're doing all the calculations needed. At the top, we have our output, which is like y1 and y2, which will be the predictions at every step. Okay, so how does this memory mechanism works? Look at the red arrow labeled store. Okay, this red arrow, after the network processes the first input x1, so the results from the hidden layer isn't just used for the output y1, it's also stored in the memory. Okay, it's represented here as alpha 1. So the memory can also consider it as another input. So we're actually just adding a new input to our neural network. In the components, we have two major components. We have the feedback loop and we have the hidden state. In each step, the network considers both the current input and the hidden state from the previous step. So like just we did explain right now, we just add a new input that represents the states from the previous state. So this is a mathematical formulation about the state ht at the state ht. So the hidden state, which is the memory at every time step. We calculate the current state by combining the previous state ht minus 1 and the current one. So this allows us to remember what has been seen in the previous steps. Okay, the same function and set of weights are used at every single time step, allowing the model to apply the same logic across the entire sequence. So we're calling this an entire sequence. Although this is a very, very intelligent way to actually take into consideration what's in the past, we have a lot of limitations on the RNNs. The first or the major limitation is that the RNN are struggling to remember the informations when we have a very long sequence, when we have a very long sequence. We call that the vanishing gradient problem. Okay, so imagine it like a phone, like a telephone message, or like imagine it as your WhatsApp chats with your friends or whatever. When you start going deeper in the conversation, you actually your mind starts forgetting what was in the first messages, or maybe don't remember what was the details of each thing, which can lead to like losing some informations in this past sequence. So this makes it difficult for the network to connect events that are far apart. Okay, so if we're talking about like in the first site, we were talking, me and Ayub or Baha, where we are talking about what we will do on day 5. Okay, we start detailing, and then at some point we will forget that we did actually want to include the transfer learning. Why? Because like that was in the first sites of the conversations. So this is one of the limitations that actually the next model uh, is solving. So when we want to address this, this is a more advanced architecture that was created called the LSTM, long short-term memory network. Okay. So in the first bullet, we say, what is the goal? What is the goal that we want to achieve? Sorry. Which is the key innovation. So we wanna actually add a more complex internal cell structure instead of just a simple recurrent network. Okay, on LSTM, it contains some special components. We call that gates. You can think of these gates like a sophisticated control system. They actively regulate the flow of the informations, deciding what to remember, what to forget, and what to output. So it's not like a memory or a hidden state that remembers and then forget when the context gets long. We have a more sophisticated architecture that remembers only what it needs to remember. It decides what to actually forget and what to remember. This is the key innovation of the LSTM. It has two major components, the cell state and the gates. Okay, when the gates, this is where we're controlling. علاقة الله أكبر. سمحنا الدقيقة الشباب. Yeah, so let's continue about explaining both the cell state and the gate. So you see the horizontal line across the top of the diagram. Okay, let's just wait for that animation to finish. So that horizontal line, this is what we call the cell state. Okay, it's a long-term memory conveyor belt. We call it technically. What is this conveyor? What does this conveyor belt does? It carries the information through the entire sequence, so that the LSTM will have the power to add informations to it or remove information from it at each step. This is what we call the long-term memory. Okay, so how does actually the LSTM control this memory? That's the job of the gates. So you can think of them like as a series of mini neural networks that acts as a regulators or gatekeepers, yeah, for the information flow. Okay, so let's look at them one by one. Following that flow in the diagram, the first cell, which is the forget gate. The job of this forget gate is to look at the new input and the previous memory to decide if any old informations on the conveyor belt is no longer needed and should be discarded. It's like a multiplication step on each cell state line. Next, we have the input gate. The input on what should be and what should be stored. It doesn't actually control what should be discarded. Okay. It determines also what new memories to get written in the cell state via an addition step. The cell state, like once that cell state is being updated, we reach out to the output gate that will actually decides what part of that long-term memory is relevant right now. Okay, so it does actually filter the cell state, and produce the output in the hidden state for the next time step. So just as a summarization, because I know this may look a bit complex, but it's not. So the entire structure of the LSTM, so it's like a regulated flow, if that makes sense. So it's like forgetting, inputting, and outputting, just like that. So what to forget, what to input, and what to output. This is what gives actually the LSTM the power to learn large context and to actually have both long and short-term memory. This allows us in real life to actually track dependencies over like hundreds of steps, over like a controlled window length, etc. Where do we apply actually those RNNs and LSTMs? So we actually the streets tend to apply these in most of like time series problems. Okay, in time series problem, the LSTMs and RNN applications, those were that was where I did use that more often. I did actually, which is a fun fact, used an LSTM network in some microservices of that tennis AI app we have. So we want to actually know in a video, according to multiple images. So a video is like a lot of images that are playing in some FPS. How many frames per second? So in that video, the goal was to know which movement you are playing in the tennis. Which tennis movement are you playing? Sorry, are you playing a serve? Are you playing a backhand, a forehand, etc.? So I cannot use one single image to know which type of movement you're playing. I did use that long-term memory network to actually combine the states from the previous images to know at the end what was the movement that you were playing. That's one of the applications of LSTMs. We do apply that also in text. Well, before the transformers, the RNNs and LSTMs were, especially the RNNs, were the most widely used before that breakthrough of the LSTM of the transformers. We also do that in language translation, video analysis, medical diagnostics, etc. On the LSTM for finance, we have the time series predictions, portfolio optimization, credit risk, etc., etc., etc. Well, the workshop of the CNN was normally supposed to be after the finishing the fundamentals, but since we have that here, I don't know if we have some questions before we move on to the next big topic, which will be the transfer learning. Were I too clear actually to not have any question?
Yeah, check the chat. We have some questions from Robert.
So it's not like the most innovative. That's a philosophical term. Okay. It's more like an opinion. If I tell you like what's the most innovative, the most innovative algorithm out there in the internet. So it actually depends on which use case you have. Okay. So I'm not buying a Ferrari to drive it in an off-road. That will be a disaster. That will be a very bad disaster. So if I wanna drive in an off-road, I would like to buy some car that was built to do that specific task. Okay, so we can use MLP for 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 uh, for some sequential data. We can use the multi-layer perceptron, but it will not give any result. The model will not learn because why? Because it's not suitable. But does that mean that it's not innovative? Not at all. Yes, exactly. So whether it's like even linear regression, random forest classifier, or CNN, RNN, I don't know, go into some more advanced techniques, that the results is what matter. And for the results, we have an architecture for each. You can even find inside that in some context, in some use case, or depending on the data points we have, sometimes we can find a machine learning model outperforms an SVM outperforms a neural network. So we actually like when you see like 90 or 95% of the papers on archives about the computer science, about the AI, etc., you'll find them always doing some benchmarking. Okay, when they invent a new technique, they compare it to the previous ones in some specific data set. Or when someone gives us some data, we have some data set, we apply a lot of algorithms to know which one did better. So we don't actually select one and we say, yes, the LSTM is the best one for the stock analysis or market stock, portfolio management, etc. And we always use it. Before deciding what's the best model, this is the workflow of a data, the life cycle of a data science project. Okay, so the next phase, or the next phase is the most, I think, the simplest one across the entire the entire presentation. She will be talking about the transfer learning. Okay, I know all with this new wave of vibe coding and stuff, people don't want to start from scratch. Okay, and this was a huge problem in the machine learning context or deep learning context. To train some advanced models to have higher accuracy, we need some very extensive, clean data sets. And that model that we will train, it will just know that specific tasks that it was trained for. And that was a problem because when you want to train a model, you need to find a data set. If you don't find it, you need to build one. And to build a data set, there is a very huge set of roles that I think we will be covering data engineering with the HEL workflow, extract, transform, and load. But that's why actually we have the solution of the transfer learning. The transfer learning came here to create what we call the pre-trained models. Okay, so how does that differ from the traditional way or the traditional old way? Okay, so Robert, how old are you? If you want to answer, of course. Well, let's say you wanna you are watching
I'm 55. I'm sorry, I'm 55. I put it on the text.
Oh, sorry. Yeah. So let's say how would you like, let's say, let me look for an example. Yeah, so how would you change like the channel you're watching on a TV? You're watching a television, you're watching some UFC fight, and then you wanna move on to watch something else.
I
Okay.
click the back channel, the channel that I was watching before, so I can go back and forth and back and forth. One click.
Okay, great. So for me, I wouldn't do that. I would just say in voice, and the TV would change it for me. The old way,
Okay.
it requires a massive data set. needs a huge amounts of computing power and time, which I already explained. Every new task starts from zero. So every time you need to restart the weights, calculate all the weights. In the transfer learning way, we start already with a model already trained, a pre-trained model, we call that, okay, on a large general data sets. On some data set that, if we have images, we will have some model trained on the unit data set. Is that the right name? Anyway, that's a very huge data set with 1,000 class. Okay, we will have that pre-trained model transfer, and then after that we will have, like, we want to transfer the knowledge to a new specific task. We don't want to classify all those 1,000 classes. We want to actually just class like 3 or 4. But the model, when it learned to actually classify those 1,000 classes, it did learn with that the meaning of an image, the colors, the features, a lot of stuff that we don't want to start from zero to actually train a model that will learn that from the very beginning. So it's like a chef using the general knowledge of cooking to quickly master a new recipe. If I have, like, I don't know how to cook. I don't personally know how to cook very well, except for like some eggs with matisha. But if some master, if I wanna, like, let's say I'm in a competition and I wanna like prepare a new recipe that I never did before. Me and a master of experienced chef, and he also never saw that. Who do you think will make it better and faster? It's actually the chef. Why? Because it has a previous knowledge about cooking, about the general use case. We have some famous pre-trained models for each of the big uh, tasks that we have for images, for the data types, sorry. So for images, computer vision, we have the ResNet, the VGG16, Inception, and EfficientNet. For the NLP, we have the BERT, bidirectional encoders, the GPT series. The GPT-2 is an open source model that you can fine tune on your own, and the T5, text to text transform. The last T I do always forget. But that's a model that can generate texts. Those are the old generational text generational models before this new era of the transformers and LLMs, etc. For the sounds, we have the Wave to Vec 2.0, the VGG-H, and the Yamne. How does that actually work? Theoretically, just a simple theory of it, because the algorithms of transfer learning are a lot, but the concept remains the same. Okay, so the transfer learning was created before because, like, the neural networks, we found out that the neural networks can learn simple reusable features like edges, colors, etc. We freeze these early layers. So we have those early layers. Let's say, let's pick this image right here. Can I zoom? Yeah. So those are all the layers of our pre-trained model. Okay. We just have some trainable layers that those weights will be the only weights that will change. Okay. And that how it works. So we just pick the last layer, and not always the last layer, but we pick one layer or two layers or whatever, and we just change that without changing the non-trainable parameter. For images, we pick the images for the workshop, the images fine tuning a model on images. There are like that's very simple. The transfer learning is very, very simple. Okay, we did choose for today's workshop the RoboFlow and the YOLO. Okay, so the platform is RoboFlow and the model is the YOLO model. You only look once. Uh, let me see if I can share my screen to show you. Okay, so this is the Ultralytics docs. Okay, which where we have in which we have many many types of tasks that we can do, like object detection, like instant segmentation, and the pose estimation, the human pose estimation. How and to do whatever task, we need data sets. Data sets for images are most likely to be found in the universe of RoboFlow. Okay, so just type some data set you need for computer vision projects, and you'll definitely find something for that. Uh, let's pick one random. Let's pick one random data set and let's try to use it. Do you have any specific use case in mind that we can actually look for some data set and trying to train our computer vision, fine tune our computer vision model on it? Let me see the chats. Walking upstairs. Okay, so we do take this data set as an example. Let's see the images we have in it. We have people. We wanna actually. This is an object detection data set that actually detects the people that are walking. So this is how our data set looks like, and we want to train our model. So what do? We go to let's see if we can actually download it. No, dataset. Yeah, this is dataset. So we want to download this dataset, which is walking 8 laws dataset, etc. And popular download formats. Let's choose on the format that we will be using. YOLO V8. Okay, get a code snippet. We want to download the dataset. So the RoboFlow universe gives you a direct code that you can just call and use on your code. Okay, so it will give us a set of lines of code that we can use. This is the API key hide. I don't want to use to see it. And they give you the actually the code to actually like download the dataset. So you want to copy this code, go to somewhere where we can run code, and paste it. So this installs the RoboFlow. This initializes RoboFlow with the API key. This is the project. The
Hey,
work
Yusuf,
project.
can you share with us the other tab? Yeah, now it's good. Now it's good. Thanks.
So yes, we did copy this. We This is the code that actually RoboFlow just gave me right now. Okay. We choose. Well, this actually installs RoboFlow and downloads the dataset under the YOLO V8 format. Wait for some few seconds for this code to be run. So now it's installing the RoboFlow, and then it will download the data. Okay, yeah, so we're done right now. It did download the data. Let's see where we have that data. Yeah, walk-in one. We look for the data YAML, the data YAML. If we go to this file, sorry. if we try to open this file, it has what are the classes that we have, the number of classes, the name of the classes, and this is a license, etc. The path for the test and the train and the valid images. So we want to actually modify this data.yaml, copy the path of the test, put it here, copy the path of the train, and the valid. Oh, sorry. Good. The second code we have is a code that will download the YOLO 8 large model, small model, XL model, or even the nano model. We'll use the nano model to speed up. You just need to change this N for the nano, S for the small, L for the large, and X large, XL. We install the Ultralytics library, and then we put our part of the data.yaml here. So on the train, on the model.train of YOLO instance, we have a lot of parameters that we can input in the code. We have chosen like the most or the easiest one, the size of the image, the batch size, and the device. Use GPU if available, is else CPU. We don't have GPU in this environment, so we'll just use CPU, and we'll use this image size and 16 as a batch. So let's train this for just one epoch, just for educational purposes, and let's see what we have. Still waiting for Ultralytics to be installed. Yeah, in the meanwhile, we have some questions.
Yeah, Yusuf, I have a question, please.
Yeah, sure.
The website about the image dataset, can you show us the website or share with us the link?
Oh, yes.
Yeah.
This was a randomly picked dataset.
Yeah, I know there are lots of premium dataset. Yeah, for example, RoboFlow, you have an API. Can you tell us about the usage, the limitation about, because we have an API? How many dataset we can use, etc. Yeah.
RoboFlow is an well, it's not 100% open source. You just need to create your account. Our dashboard will look something like this. Okay, workflows, monitoring, deployment, explore, etc. So when you click on explore, you have this. Yes, sir. Okay, this is the RoboFlow universe, they call it, where you have a lot of data sets. When you create your free account, you have all the access of the free data sets. People that did upload their data sets here for free. Okay, there are some premium data sets, advanced ones, that you need to pay to get that. So your API key gives you access to all of the free data sets without any limitation. But when you pay, you have access to some more premium data sets.
Yeah. Okay. Thank you. Thank you.
In some data sets, you can find even some pre-trained, some people that did train a model and did upload it here. So you can see even you can upload directly, like select file, I don't know, put some face in it, and it will do the inference here in the platform. You can switch the model if you want. Those are the metrics, the map, recall, precision, etc. So this is a very, very powerful universe that did simplify the computer vision. Try it on my machine, and they will give you the code on how to do it. Okay, let's see if our model did. Yeah, so the installation was successful. We want to now download the YOLO Nano model, the V8. There are 11 versions of YOLO, maybe more, and with different sizes. So this is the architecture of the YOLO model. And now, let's see, it's being trained, freezing the layer, train, fast image access, read, etc., albumin mutation, optimizer. And now it started to training. If you switch to, you can actually select the optimizer you want. You can do a lot of stuff with this model.train. How much time? So it's 3 minutes, and the first epoch will be done. We'll cover some questions while we're waiting for that, because I want to show you actually when the training is done, how do you find the output. So if you can see here, this is the YOLO V8 Nano model. Yeah, it's just 6 megabytes. And those are the runs: detect, train. Those are the weights of the training. This is empty because the training isn't done yet. Those are the arguments YAML that we did use: the task, the mode, exist, okay, etc. Those are, you can actually control all of those arguments inside your dot train. Okay, dropout, validation, split, save, JSON, etc. You have the labels. This is an overview of your data set. And this is all automatically being done by Ultralytics by just running this YOLO.train, model.train. You have the labels, instances. You have only instances because we have one class. You have the train batch. This is 16 images where we have the class 0. We are detecting people that are working. Train batch 2 and train batch 1. So when the training is done, the testing will be done also automatically, and also the metrics and the results of your training will be available. How do you know which version of YOLO you'll use? Yeah, that's a very, very good question. Let me share this screen. I was here on the Ultralytics models. You can simply know that by looking at this graph. And those are the results. Well, and that's also a tricky question, because those results that you see are the one on the COCO dataset. Okay, so the YOLO was tested on the COCO dataset to give you these insights, but that gives you a more insight about each version. That doesn't mean in some datasets you may even find that YOLO V5 will be doing better than YOLO 11, but that's very, very rare, if that's the term. So those are the models you have, and also you have the segments anything model from Meta that segments actually anything, and you have your segmentations masks really. Yeah, so let's go back to our workshop. Share this tab instead. Yeah. This is the curve results. This is new. This wasn't in the previous version of the API. box, confusion matrix, etc. So now you see on our training directory, the text, this is the first one, train. Those are the weights of our model. This is the best model, .pt, PyTorch. This is our last trained model. We only trained that for one epoch, so that means the best is the last year in our case. You have the box F1 curve, the box PR curve, confusion matrix. This is the confusion matrix normalized, train batch, etc. So those results are not the best results we can get because we only trained that for one epoch, but that gives you an overview of the power, how powerful ultralytics combined with RoboFlow is in computer vision context. Okay, of course you can also train your own models, but when you have a data set like this, like the one we did use right now for the walking here, how many images we have? We have 245 images. That will never be sufficient to train an algorithm or a model from scratch. And that's the beauty of the transfer learning. Okay, so let's go back to our presentation and let's continue with it. We did fine-tune our YOLO. So I'll share this notebook for you, with you guys when we were done, right, Baha?
Yeah, sure. When we finish all our session, we're gonna work on a Google Drive with all the certificate and the notebooks links, the resources, and the slides. Yeah.
Great. Okay.
I have just one question. I have just one question, Yusuf. Can we test the model?
Uh,
Isn't a random working picture from Google, something like that? Yeah. We can generate a code or something like that, if possible. If not, it's okay.
okay, so we need to write the code for that, and we need to go to see the documentation. I'll share. So when we're done, I'll just add that to the code and share the notebook with you that has also the inference code in it. Okay. Uh,
That's great. That's
it's
great. Thank
model
you.
it's model.predict or something like that. So that will take us some time. We are already like 5 minutes left in the timeline we have.
Yeah,
Okay.
yeah. Feel free. Yeah.
Yeah. So we have the last part of our meeting today, which we called the bridge between humans and machines, an introduction to NLP. Okay. So I have a question for you guys that I wanted you to answer me. So I saw a man, this sentence, I saw a man on a hill with a telescope. Who has the telescope? Me or the man? So that's actually why the NLP is very hard to explain that to machines. Okay. Even someone that is a beginner in English, or sometimes when you're talking to a friend, one sentence can have multiple definitions, multiple meanings, etc. And sometimes it's very ambiguous. So that's why we have this. That's why the NLP is hard. Natural language processing is very hard. To simplify it, we have two parts on the NLP, what we call the NLU, the natural language understanding, and the NLG, the natural language generation. In understanding the text, we have sentiment analysis. We want to understand, is a product review is positive or negative. A named entity recognition. So we have a huge paragraph and we want to know what are the people mentioned in that paragraph, or what are the places mentioned in that paragraph. And this is most widely done using Spacey library. We have translation, Google Translate, DeepL, okay? And then we have the generating text, which is the second part of a second use case of the NLP, text summarization, question answering, code, code completion. Uh, Now we'll move on to the breakthrough 2017, the transformers. Okay, the architecture of the transformers was introduced. So the transformers processes all the words in a sentence at once in a mechanism using a mechanism called attention to weigh the importance of different words to each other, no matter how far apart they are. Okay, so when you give ChatGPT that works with a transformer, if you give it some long prompt, it understands it in one way. Okay, it understands all the words in that sentence at once. It does not it doesn't work like the RNNs where it just pick the previous ones. Okay, or processes just piece by piece. This is the paper. Attention is all you need, and it's really the attention is all you need when you're reading the paper. Okay, so the difference between the RNN and the transformers, the RNN is suitable for sequential processing tasks, but many struggle with long-range dependencies. Okay, transformers, it excels in capturing long-range dependencies through attention mechanism enabling parallel processing. The difference between the features of the RNN and transformer, the RNNs are working in a sequential mode, so it's like word by word, and transformers are parallel context mechanism. A hidden state is passed from the one step to the next. The attention mechanism on the transformers is a self-attention, direct weights the importance of all words against each other. So it gives every word a weight. Key strength. So it's conceptually simpler, effective for shorter, strictly ordered data. And the transformers are very excellent at capturing long-range dependencies, highly parallelizable for faster training. Key weaknesses: the vanishing gradient problem that we did mention before, forgets long-term context, slow due to sequential nature, computationally intensive with very long sequences. So we need a very huge model GPUs to actually use or train or to do the inference on a transformer-based model. I think you will continue the rest of explaining the transformers, right? Ayub?
Yes, well, you did explain it well as a start, because we said that you will be having the chance to explore transformers more later. Okay. But anyway, just going to say some. Let me just share my screen. Isn't now. Okay. Perfect. Yes. So mainly, this is how a transformer looks. It has two main parts. The first part that gets the input. Input gets something called embedding, which is transforming the written word into a vector with numerical values. Then we do something called the positioning the location of each token. So transformer is not like RNN. RNN knows the position of each word in the sequence, but in transformers don't actually know. So we need to add this step to tell the transformer the position of each word. Then we do some self-attention mechanism, encoder. This is all we're going to discover. It's a big topic. That's why I don't want to go into it. If I go into it, it's another hour, and I need to go home. I'm still at the university. Yeah. So then we have some calculations, etc., etc., and we have the other part is where we give the output or the expected output. This is in the training, of course, the expected output. And we do the same thing, self-attention, decoder, feed forward. Then we give the output. Why this? You notice here it's shifted right. This is just to help with the training. It is what makes transformers train in a parallel way. So I really want to explain, but I hope next sessions with the generative AI sessions, you would ask them to explain transformers, or please ask them to explain transformers and why we shift right, how we train, etc., etc. Because it's a big topic. Okay.
Okay.
Okay. Because I really want to explain it, but anyway, I just want to show you a quick practical case, so you can see how we can use transformer to generate next word. So you can have a code in your hand, you can work on it, etc., etc. I'm just going to find the collab. I think it's here. No, here. Yes, here. Share this tab instead. Connect. Okay. Can you see? Right. So yeah. So first of all, we install the dependencies which are the PyTorch transformers. This is a must when we are working with something in the transformers library. We are going to work with a simple model like GPT-2, which is like one of the most basic models. It wasn't. I don't think it was published to the public, like given to the public to use. It's until GPT-3 or 3.5. GPT-2 was never used by us, by users. But it was like the beginning of OpenAI and the beginning of knowing how we can make our models better. Yes, so here we just import the models. We import the tokenizer, which is, I think, something that was explained by Yusuf, which is the model, exactly, GPT-2. And now we do some next word generation. We have this example. Welcome to the Open Data Science Conference. It is, and we want to predict the next word. First of all, we do is we tokenize this sentence. We have here welcome, for example, is represented as this number, 2 is as this number, the as this number, etc., etc. Then we
Sorry, Ayub, can you just make a zoom in? A 3 zoom in? No, with yeah, it's okay, but if you want the full screen, yeah.
okay.
Again, 2 times. Thank you.
Okay. Yes. So I said we have this example. Welcome to the Open Data Science Conference. It is first thing we do is we tokenize this, and we do some. This is these are the tokens we got. Of course, we are using GPT-2 as a tokenizer, which is a pre-trained model. So these are some representations of these words in the space in that model. Yes, we make it into a tensor because it's more model friendly. Then this is not really important. This is also not really important. We go move forward to the things. Yes, here we are going to make the predictions. This is the size of the prediction, or the shape of the prediction. I'm sorry. Then we show the prediction. The prediction is you can see that the predicted next word is okay. So our model have successfully predicted the next word. If are working in a real case where we are going to generate a paragraph, a sentence, or something, this thing that happened here will happen over and over and over and over again. So it's basically the same concept, but it is repeated multiple times, so until we achieve the stopping point. Yeah, this is another example to give like a paragraph or sentences. It's the same thing again. We just give like the start, the first sentence. natural language processing is slowly becoming. We know Yusuf has said that the processing is done in parallel. So all these words are fed into our transformer at the same time. This is the power of transformer in comparison to RNN, for example, as mentioned before by Yusuf. So this is what allows our model to be more context respected, and giving relative and really good answers. So natural language processing is slowly becoming, and I want to give sentence or sentences. Natural language processing is slowly becoming. The prediction is more and more popular. For example, and some other not really good information and not really related information, because remember that we're working with the GPT-2, which is not that good. We're going to see an example. If we change this to another sentence, it's going to be worse. Notice here, it was like the first step is to create language processing program that can be used to create language. This is called language processing program. This language processing program is a program that can be used. So it's coherent. It's not the best, but it's coherent. It's related to the thing, to the start thing. But here, the start sentence. But here, if we change the sentence to something, for example, I am. What is this? Okay. I am really tired today. I really need to drink, for example, some, and we let it. Hopefully, it's still running. No, I need to rerun everything. Okay, let's run all. Yeah. No, it's going to take a lot of time. Yeah. So it's not really important. If it did run, it's good. If it didn't, you can play around with your own starting sentences. And what I wanted to show you is that GPT-2 is not the best, of course. It will make mistakes. It will make a lot of mistakes. But now, hopefully, we have a lot of better models. Like we have like GPT-4o1 and DeepSeek R1. We have Grok. We have all these models that are capable of generating very long sentences and very long text corpuses perfectly. Yeah, it's going to take a lot of time. So yeah, any questions concerning this part? I know it's just like an overview. It's not really a deep dive into transformers, but hopefully they will explain transformers in other sessions. Because this, yeah, Muhammad.
تفضل محمد.
So thank you so much.
Thank you.
My question is, will Vision Transformer can replace CNN?
Yes, I will tell you yes and no. You know why? Because CNN, as we have explained before, there are some architectures of CNN, like CNN alone, like a normal CNN, like we did in the practical case, is a naive CNN. It's not that good of an architecture. But there are some architectures made by some researchers, like ResNet, MobileNet, VGG16, for example. These are very, very fast and very, very small in size compared to vision transformers. Or for example, let's just make a comparison between something I know because I did it in one of my internships. This is a comparison between YOLO in transfer learning and the LTR, the detection transformer. The
I would like also to add an information like as an answer for this question about the VIT comparing to CNN. The major problem in this comparison is the computational power. When you have a
That's what
VIT,
I was
yeah,
going to. Yeah, I was
yeah,
I was headed to
you,
that question, that answer, but it's okay. Yeah.
yeah. It's when you have a VIT, you definitely need like a huge servers to run that, especially when you have a lot of users when coming to deployment. So I would rather use a model, a CNN model that has, let's pick just the accuracy for example as a metric, that has 87% of accuracy and use it in production rather than using a VIT transformer that will give me that 90 or 92%. So I will sacrifice this 5% of accuracy just because of the cost of deployment. Does that make sense? So it's like sometimes the CNN, if you have some good data set, we always look for the lightweight models. So having the urge to always use transformers is what I actually I hate about today's community, today's AI community.
So thank you so much. So this depend on the cost of deployment. So,
Yeah, it depends on what you want for deployment. If you prefer accuracy and you have big servers, yeah, sure. But you can use like transformer-based solutions. But if you want fast performance and good accuracy also with CNN architectures, we are going to go with CNN architecture.
okay, thank you so much.
Yes. Yes, Ayman.
Go ahead.
Like Salam, I have a question.
Yeah.
When we use a neural network model, how do we find the right hyperparameter that perform better, that have the better accuracy?
Yes, this is a very good question. Very good question. When it comes to CNN and finding the best hyperparameters, there are some ways, some algorithms to find those hyperparameters. One famous one that I know is grid search. Is a function, or we just call it in the code. It's called grid search. It's the one that helps you finding the best parameters. What does it does? Basically is try multiple parameters and compare them to find the best one, which is not very practical. So there are some other complicated, mathematically complicated solutions in optimization. For example, I don't know if you have studied before something about optimization and uh, meta-heuristic approaches or something like that, or heuristic approaches. So yes, random search also. So these are methods also used to find the best parameters, like heuristic approaches and meta-heuristic approaches. I'm sorry, just heuristic approaches.
Okay, thank you.
It's recherche opérationnelle. If you want to learn more about heuristic approaches, is under the recherche opérationnelle course. You can look. I don't know what is it in English because I studied it in French, but yeah. Yes, algorithm génétique, etc., etc. It's a part of the recherche opérationnelle.
Yeah. Well about the question فوقاش نستعملوا هذه وفوقاش نستعملوا هذه. Alors كما قال يوسف, it's all about الكمبيوت. فوالا بحال عندنا ال ال ام واش نديرو ديال 700 بليون بارامتر ولا نديرو واحد سمول لانجويج موديل ولا شي حاجه. بيان سور اللي تيكون صغير ما تيكونش زعما داكشي زوين بزاف الاكوريسي وداكشي. غير هو about problem solving. انا جو بريفير تبدا من البيزكس. يعني راك تلاحظ واحد تكست جينيريتد باي شات جي بي تي مع 10 ونص بالضبط. دونك كاين الاي ان ان اللي خرج في 1950، ومن موراها كاين الار ان ان خرج في 1980، السي ان ان خرج في 1989، وقبل منه if I remember يان ليكون في 1986 في ديك لي لاب ديال بيل كان دار ديك ليكزامبل ديال ديك الداتا سيت ديال اللي تتعطيها الارقام تدي لها بحال الاو سي ار. دونك سي ان ان خرج قبل شي شويه، والال اس تي ام في 1997، وموراها الكرو، وموراها الفي جي جينيت، وموراها موراها في 2017 ترانسفورمرز، وموراها الايفيسينت نت في 2019، ومن موراها الفيت في 2020. وخرجوا بزاف وباقي يخرجوا. غير هو انا تيجوني هادو اون فيت هادو دي ليبريري دي زاركتيكت دي زاركتيكتور، ملي تيقولوا دي زاركتيكتور ولا دي زالغوريثم سون بحال لي ليبريري. دونك الناس اللي دايرين الكودين تعرفوا ان لي ليبريري ملي تخدموا بهم ولا تمشيو تخدموا ميم باغ اكزومبل بشي فريم ورك مثلا لارافيل عنده ليميتيشنز ديالو. دونك مثلا تكون خدام شي سيت tu peux pas trouver toutes les fonctionnalités اللي انت محتاج. مثلا خدامين بلارافيل راه ضروري خصنا نديروا دي تروك مانيوال بالبي اتش بي. والدراري اللي تيديروا مثلا ديك الكودين جيم وهذا اللي تيخدموا بالسي بلس بلس خصنا ضروري نخرجوا واحد الاوتبوت بواحد التايم قليل وبواحد الكمبيوت قليل ويكون نفس الريزولتا ولا شي حاجه بحال. دونك دي فوا سي بوسيبل الواحد ما يخدمش كاع بالبايثون، سي بوسيبل يكري كلك شوز فروم سكراتش كاع ميم بالسي بلس بلس ولا بالراست ولا شي حوايج الا كنتي تو بيان كومبري l'architecture. زعما تنقولوا for some context اللي more advanced وهذا des fois pour زعما tu peux faire ton code propre à toi تعطي واحد الريزلت احسن. وهذا الشيء هو اللي وقع ما بين ديبسيك وشات جي بي تي. منين ديبسيك خسرات 6 المليون مثلا، وشات جي بي تي والفيرسيون الاولى ديالهم هذا ديما تيخسروا مثلا 300 مليار جو سي با جو دي نابورت كوا، باسكو هما داروا افونساو بزاف في المات وداروا ديك reinforcement learning based on human feedback وهذا. يعني توجور عندنا بروبليم في الاوبتيميزاسيون ديال الكود، والا كان داك we have a good data scientist اللي عندهم واحد نوليدج هربان في المات وقراو واحد فورماسيون دو كاليتي اكسيتيرا، راه فو بوبي ترافاي باي حاجه وتوبتيميزيو احسن. واكشولي راه واقع اون غير ما بين اوبن اي اي وميتا. الوغ زادهم 20% سام التمان في السالير وعطاهم كاع دي بريم ديال 100 مليون ديالنا ولا دولار نامبورت كوا، وباش يرتاحوا حيت كانوا تيخدموا بزاف عطاهم واحد السيمانه عطله. دونك في ديك السيمانه عطله مارك استغلها ومشى تيصيفط البيج برينز ديال اوبن اي اي باش يهايريهم وتعطيهم لايك الشيك على بياض. تيقول لهم يعني كان واحد خونا لايك غير الساروس غير الحلاوه ديالو اكثر من داكشي ديال لاعبيه الكره اللي كنا تنقولوا لاعبيه الكره هما زعما داكشي فابيلوس شحال تيشدوا اكسيتيرا. دابا سي لو طون ديال العلم وديال we need some genius data scientist. So yeah, as a data scientist you should use all methodologies all methods وتكومباري بيناتهم داخله في البنش مارك. يعني تخدم بهذه وتخدم بهذه وتخدم بهذه وتشوف شكون اللي احسن على حسب اليوز كيس ديالك. تاسيت
يا بالنسبه لهاد القضيه ديال كيفاش كنديرو بوست ترينين وكيفاش رينفورسمنت ليرنينغ كترد لي موديل حسن which was by the way the talk اللي كدرت الصباح. so maybe في MDS عرضوا عليا مره اخرى ندير هذا الشيء هذا maybe نقدر نشرحه لكم ما تبقاوش محسن منه. so maybe next time we're going to talk about that قضيه. so if yes Mohammed.
So my question, what is the type of transfer learning? Because I think there is a lot of use case, so we cannot focus on just one type to do all these use case. So if you can tell us about the other type of transfer learning and the specific case when we need it.
Yes. So if I understood your question is what transfer learning can do. Transfer learning can be used if we had some model who is trained on a task, and we want to add another task to that model. For example, we have a model that trained on classification, and we want it to detect objects. So detection is another task. This is the type of transfer learning. There is also another type, which we have a model that is in the same task, but we want to make it. For example, if we have detection as showed in the practical use case, if we have the detection, we have a model which is YOLO, which is already trained on detection objects, but it has not trained on detecting human beings, for example. But it is. Let's say it's not trained in detecting this bottle of water. Okay, this bottle is not in the classes that is trained on. If I added this class in the training, I made the model capable of detecting this class. This is also called transfer learning. Is this what was your question about?
Okay, thank you so much. Thank you.
The most important thing that we don't need to train the model from the beginning, as mentioned by Yusuf. We don't need to train the model from the beginning. We just take a pre-trained model and add some layers to make it adapt to other tasks. Will adapt to other classes, for example. Other questions? Yes. So guys, if there are no other questions, thank you so much for having me for MDS, and thank you, Baha. Thank you to all the team behind this amazing conferences and community too. I really love seeing communities like this growing bigger and bigger in Morocco, because this is something that makes us very proud and makes us want to share information between others. Today I am a speaker. Tomorrow maybe Muhammad or Ayman or Bahija or Hassani, Iman are going to be a speaker, and they're going to be here to understand and try to understand and discuss what they have to say. So guys, I hope you enjoyed the session and you learned a thing or two. Of course, if you have questions, you can reach out to me. I attached my LinkedIn in the messages, or you can ask me anything. Thank you.
Yeah. Thank you, Ayub. Thank you, Youssef, for this session. So it was very informative, lot of knowledge. Thanks a lot, and see you next فوقاش شوية نشوف الكالندر الأربع الجاي 9 جويي فوالا. and that's it. اللي مازال ما داخلش معنا في كاتريام جروب راه لقينا له ليان. and yes, that's it, I think. Merci bien. See you next time. Yeah, Yusuf, if you are with us, you can give a last word. I don't think so. So yeah. با ايوب تهلا تنديروا شي قهوه في الدين ان شاء الله. يلا تهلا.
مرحبا.
الله يحفظك. الله يحفظك.
الله يعاونكم. السلام.